Like growing up, she practices. That's right. First flight was here. I was here. Okay.
Okay, I want to welcome everyone. My name is Lynn Jensen. I'm the treasurer for the Los Angeles section of the AIAA. And how many here are members of AIAA? All right. Yeah, it's a place to be in aerospace. This is where all the information is accumulated and cataloged and categorized and distributed to people in the industry and others who make decisions about the industry. So we got a special program. By the way, I wanted to let you know that the presenter, Dennis, is the career development lead on the board for the Los Angeles section of AIAA. So you really want to get to know him if you're interested in career, or if you're retired and you want to get back in.
Sure why you would, but okay.
You never know. I worked for Northrop Grumman for 44 years, and before that with the CIA and also on the Minuteman ICBM guidance system. And let me tell you, aerospace is the place. It was a career that was just so fulfilling. I was just grateful every day. I had to pinch myself sometimes just to. It was so good working in aerospace. So with that, I'll turn the time over to Dennis, and I can't wait to hear what he has to say.
Fantastic. Thank you very much. So just a quick introduction on myself. My name is Dennis Leon. I've been in this industry for about 26 years now. Most of it at Northrop Grumman, about 21 years there, building spacecraft. But I am going to talk about one of my interesting projects that I did earlier in my career called the X-43. Before this, I actually worked on the Trident II ballistic missiles, the sea-based version of yours, of the Minuteman. I did the Trident II under the sea, then I went to air, and then now I'm into space. So I kind of literally progression my way up on the ladder here. So what I'm going to talk about here on the X-43 is I'm going to keep it kind of top level. I'm not going to really go into extreme technical details or anything like that. I was more on the operations side, so I'm going to share how this was built, a little history on it, why it was done. I'm going to share some stories. Hopefully they're entertaining. Some may be a little disconcerting, but you know we'll get through it. This is the entertaining and exciting part of working in the aerospace. Awesome. So let's get started.
Yeah.
Off your meds real quick.
Thank you.
There you are.
It's not working, Ken?
Yeah, once it comes.
Okay.
Sorry about that.
Okay, there we go. So the X-43 was a HyperX program, started around 96 when they started the design. It was, oh.
Need to share the screen.
Okay?
Yeah.
Okay, perfect. So the HyperX program was a relatively small program that was started at Dryden. Well, it's called Armstrong now. I still refer to it as Dryden up at Edwards. But it was a collaboration between Langley and Dryden. Fantastic organizations to work with. I mean, it's probably some of the most fun I've had over there. But this is about a $230 million program, started in 1996. Very exciting, very unique. This was essentially a B-52 bomber dropping a rocket where another ship separates and takes off from it. So it's almost like three parts. And you can see here, there was 3 different flights. First one failed. We'll talk about that one. Second one did hit its 6.8, which was designed for Mach 7. And then the third one hit 9.6, Mach 9.6. So very exciting times here. Is it still not working, Ken?
One second. It should work.
No, it's not working.
I'll pick it. Not working.
Okay, notice. Okay, perfect. So what was the motivation for HyperX? So it was a research program, but a lot of the motivation was, let's just see how fast we can go. So this is testing of materials. So there's different kind of materials on here, but it's also for future flights, future options, right? We're doing research on how fast we can go, because this is one of those where we haven't gone this fast before. So is the materials going to melt? Is this thing going to just go fly off the rails, right? So a lot of this was base research for anything that's coming forward. And you'll see that as we move forward too. So what is the main point of this? So a lot of it was, really understanding at Mach levels, what does the flight dynamics look like, right? Just like if you're driving in a car and you stick your hand outside, either it's vibrating really fast or is it smooth, right? And so when you're going this fast in air, even the smallest turbulence can cause catastrophic incidents. And so this right here was really to decide, hey, what does the flight dynamics look like here? So that a lot of these programs, future on, has a baseline to look back at when they design their future vehicles to say, hey, you know what, this is what happened on the X-43. Let's learn from those lessons, or we take those lessons and improve upon them. And as you can see here, a lot of this vehicle right here was designed with a specific shape in mind, where the whole vehicle itself was designed so that it funneled the air into the engine, right? So this is one of the very first free-flying vehicles where the body of the aircraft was designed to funnel the air right into the engine itself. Other times it was strapped onto the side of a rocket, so not necessarily designed for it, but this one is. So when they were doing some of this testing, so there are hypersonic test tunnels, and I'm going to show this video down at the bottom here. Is there sound, Ken? Okay, there's supposed to be sound, but that's okay. You get the gist of what's going on here. So what you can see here is the vehicle flipped upside down, and this part is the engine that you see down here on this model, right? And so you can see the cowling opening up when it reaches Mach 7 speed inside the tunnel. So this is the very upfront design. Oh, there we go. So this is the upfront design when they were testing the overall shape and the engine size and everything that you see right here. So luckily they had a Mach 7 wind tunnel that we can do testing in. So what is the principles of a scramjet? Anybody know? Pretty sure some people know. Okay. So essentially the scramjet has no moving parts. Okay. So for those who are not quite familiar with engines, most engines have a spinning turbine blade that compresses air into the engine. This has no moving parts to compress the air. So what do you need? You need a rocket that you see here to get up to speed. So when the air is pushed into the engine, it's compressed enough that the compressor does that you can actually shoot the fuel in and ignite it, and it will keep on going. So this is one of those where there's no moving parts inside this engine at all. The airframe integration I talked to you about earlier was that everything here was designed so that the air flows into the engine in a specific way so that it produces the correct amount of compression of the air inside the engine itself. So what was the vehicle look like? It's not a very big vehicle. It was unmanned. So you're talking about 12 feet long, about 5 feet wide, and maybe a little over 2 feet high. So not very big at all. since it is unmanned. But the front nose that you see here, this piece right here, is a solid machine block of tungsten. And so anyone know why we have that in the front?
Heat absorption.
Part of it is heat absorption. Part of it also is to maintain the balance in the front, especially if you're going at that kind of speed, right? Exactly. And so you can see here, the front is very light, right? So that's why they're adding some extra weight in front of the nose. But the backs right here, a lot of it is covered in thermal tiles, which we'll talk about here. As you're going that kind of speed, the temperatures are very, very high. Of course, different parts have different temperatures. The front's going to be higher than the back, so you can see there's certain parts that are brighter than others, but you're talking thousands of degrees, right? These are things that will melt regular metal. And so that's why, what do? So we lean on technology that we understand. And what is technology we understand? Space shuttle tiles, right? So this whole thing was pretty much covered, or most of it was covered in these black tiles that you see here that were essentially space shuttle tiles, okay? And they were extremely brittle. And I'll show you some pictures later on of some of the damage that you can see. You can actually see some of it right here. The leading edges as well, but most of the body itself is covered in these thermal tiles that you can see here. And let's look at the interior of it. So the interior of this vehicle, I mean, it's a jumbled mess right here, but you can see this white part right here, all these, that's damage. That's when we're inside, our elbows are leaning up against it. The corners of those tiles, we chip, we break off pieces, and so we constantly have Boeing coming over to replace these things. And so you'll see later on down the line during some of the operations, there's foam padding all over the place because we can't keep chipping away at it. This is very brittle stuff. So, but you can see the tiles all the way around, all the leading edges. And this is the solid block of tungsten in the front. So what makes this thing go? So this thing has hydrogen tanks, silane tanks, and nitrogen for purge and water for cooling. So these two hydrogen tanks were pressurized to 8,000 psi each. So for those who know, 8,000 psi is extremely high for such a small tank such as this. I was talking to some of the Air Force fire department when we were out on the flight line testing, and they're like, you know, if this tank blows, you're going to blow out windows in our base a half a mile away. But I'll get to that when I get to that story. But you can see here, a lot of this, the silane and the hydrogen were the main parts of the propulsion fuel of the system here. So there's a lot of ground flight and flight line testing. What you see here is the testing of the system. So you can see some water coming down here at the bottom. So this is the vehicle itself. All of these cables are feeding power and feeding the water into the whole system. But before we get into that, let me talk a little bit about who actually made the airframe. So there's this company called Microcraft. You can see it right down here at the bottom of this model here. But it's a small little company right here. That's me. I had a lot more hair back then. So you can see how long it's been. But there's a small little company in Tullahoma, Tennessee, in the middle of nowhere. So when I first got there, they're like, we're going to Tullahoma, Tennessee. I go, where's Tullahoma, Tennessee? And look it up on the map. So it was literally an hour outside of the major city. So we flew in, and we were a bit of a motley bunch. So you have a Native American guy, you have a biker guy, you have me, and you have all these. We were a motley bunch. So we got off the plane like, we're not in California anymore. So we drove in, literally a 2-street town, extremely small. My hotel was right behind a railway. Like literally, you can open up your your window and there's the railway. Like great. So really, really small town, but these were fantastic people. Small little company. They built the airframe for this vehicle. Really knowledgeable. Here's the team of them right there. Extremely friendly, but very knowledgeable in what they're doing. They can. All right, perfect. So when they delivered it to us, they delivered it from this fixture from Microcraft. You can see here the vehicle's on the inside. So they delivered this over to us at Edwards Air Force Base. Armstrong was inside Edwards Air Force Base. And you can see here in this picture in the back, these are all of the flight connections that gets attached to the adapter right here on this model. So this is all the flight connections from the vehicle to the adapter before we separate. That's us right there with the vehicle. You can see the wings pointed upwards, but behind it is the Pegasus rocket, which is what you see here. Oh, actually, you know what? I'm going to tell you the story here. So this panel right here is the fueling panel. So we did a fueling test out in the Mojave Desert, out in the runway. So this is the runway that the space shuttle lands on. So we were probably about halfway, no, not even halfway, maybe like 500 feet out, 500, 600 feet out. And we had the Air Force Fire Department, and I looked, I'm like, man, they're really far away. They're like way down the flight line. And so I called them up. I'm like, hey, are you guys ready? No, we're ready. I'm like, you guys are far away. There's a reason for that. Oh, okay. I was like, all right, great, fantastic. So we're sitting here and we're going to do a live fire test. So there was 2 stacks. I wish I had a video. I don't have the video, but essentially there's 2 stacks on either side where we blow out and there's actually fire shooting out. So we're actually doing a live test. And somebody has to be right up against the vehicle turning these knobs. So there was 5 of us. Anybody see the movie Armageddon? Right? It was literally that. We stood there and we picked wires on who was going to be there to turn. So let me tell you who got the short one. It was this dude right here. He was like 62. We're like, you've had a long life. Fantastic. And we all ran for it. We jumped onto the golf cart and we just took off. He had a nice choice words for it. But we gave him a Nomex suit and a little welder's helmet. Best of luck, whatever that's going to help out with. Right? Because, like I said, the fire department was like, you know, if that were to blow, everything around it would be incinerated. Like, great. Because those tanks were pure hydrogen. In addition to that, the tank next to it was silane. So, and they're all pressurized around 8,000 psi. So that's just a dangerous combination all the way around. But it was successful, by the way. Nothing happened. So he did come back and, you know, we did hear about it for a week from him. But everything was successful. And you can see here, this was, excuse me. So this is the B-52. So this is NASA's B-52. So you can see all the markings right here on the side. So these are all the missions that this B-52 has done. Very interesting. It's one of the first few that's rolled off the line when they were making the B-52s. So you can see back here, the rocket is mounted. So that's mounted right here on top, under the wing. And then the X-43 right here in the front. And so you can see we're trying to protect the leading edge because, again, very, very fragile and very easy to get damaged. So you can see that right here as well. So we're doing a mating test. We're checking to make sure everything fits, make sure that we can get telemetry. So that's what we're all doing right here at this point. So interesting. I actually got to climb inside a B-52. So I don't know if anybody ever been inside a B-52. You have, so you know it's extremely tight and cramped up there. So I give recognition to those pilots that would fly hours and hours because I'm sitting in there. I mean, that chair was probably 3/4 the size of this chair right here. You're sitting in there for hours, and there's like 4 or 5 of you in there. So it's really cramped. I was surprised at that, but I actually got to go in, so that was a cool thing to do there. So what was the launch stack look like? Like I was saying before, there was 3 parts. You got the B-52, you got the Pegasus booster rocket, and then you have the X-43, the vehicle itself. So there's really 3 parts to this. And you can see right here, this is where we're rolling out to get mated onto the B-52. So this is the adapter right here on the top that mounts to the top of the Pegasus booster that goes on underneath the pylon of the B-52. So there's really 3 parts to the Pegasus rocket itself. You got the engine in the back, you got the adapter in the front, where the X-43 gets mounted onto, and then you get the pylon attachment for the B-52. So what does the mission profile look like? So the B-52 would take off with the entire stack. It would take off, it would get up to a certain altitude at 20,000 feet. It'll drop the whole entire Pegasus rocket along with the X-43. It will drop, and then it will ignite. It will begin its ascent up. Once it gets up to Mach 2 at that height, then you'll see right here in the back of the vehicle, there's actually 2 hydraulic pistons that pushes it out and separates. And so that's where the X-43 now separates, because now you've got enough air coming into the engine for it to ignite and go. And so the flight itself is not very long. People think, you know, we're flying for like 30, 40 minutes. I mean, we're going to go really far for 30, 40 minutes. So it's not a very long flight at all. It was done over the Pacific. It was done over the Pacific Ocean, and you can see here some of the separation time. So we're talking milliseconds. This is not very long at all. I talked about a lot of the flight test campaign challenges. So the first one failed in 2001 when it launched. So 13 into the flight, the rear stabilizing fin right here that you see on this model snapped off. So you can see right here in this picture, 1, 2, and then 3. So all 3 snapped off as it was going. Okay. And you can see here, it was just going down. And so then they had to, range safety had to detonate. So we had to blow it up over the Pacific. So we had to fly over the Pacific because the FAA, and they were like, please don't aim toward LA in case that thing takes off and you couldn't stop it. We don't want a, you know, multi-thousand-pound missile going Mach 10 at our city. So we're like, okay, we'll aim it out toward the ocean, right? Make sure we didn't aim toward Hawaii either, right? But what was the cause of this? So this was a little bit of an issue. The Pegasus was designed for 40,000 feet drop, not 20,000. So the air density was a lot higher at 20. And so it couldn't handle the strain. So the stabilizing fins in the back, that's why it broke, right? So once one goes, then you have a cascading error. One breaks, the other breaks, and so on and so forth. So that's what you see here. And so the fix, modify the conditions, very easy, drop at 40 versus 20, right? Increase the hinge torques. So a nice little story about that. So there was 2 actually buildings on Edwards Air Force Base. There was a hangar for NASA where we were working on the X-43. And then on another building, maybe a couple hundred feet away, is another warehouse. That's where they're working on a booster. And so for those who worked with rockets and at launch sites, you know, there's this little building, right? Before you walk through the gate, you got to switch out your badge. You guys know why you do that? Get a different one. So that's in case if the building explodes, we know who was in there, because you're going to be incinerated. No one's going to know. So that's why we switch out our badge so we know who's in there. And so in that building was the Pegasus rocket. I remember walked in one time, there was 3 big guys. They were just manhandling one of these stabilizing fins, like 2 guys just holding it right in, and the 3rd guy just torquing, cranking it down. Yeah, hey, the booster was not my thing. So I was like, I'm just going to leave it as is, right? I don't know what they're doing. My responsibility was the X-43. All right. And so what do you know? That snapped. I'm not saying that's the cause, but hey. Oh, so you can see here, here's the drop.
That's a 20,000.
That's a 20. So you'll see it break right here too. There, 3. And then watch it one more time. So you can see the right one breaks in the top and then the one on the left. Just as it's starting to angle up. There you go. So something as simple as that, 20 versus 40. So the second flight was a Mach 7 flight. So it's not a Mach, all 3 of them were not Mach 10. So the first 2 was supposed to be a Mach 7 flight. So the second one was a Mach 7 flight, and we did hit Mach 7. So with all those changes, so you can see here at 40,000 feet now, drop, ascent, and then free flight. That one was successful, Mach 7 as designed. So a lot of people think, why didn't we go Mach 10? It was designed for Mach 7, the second. And then, of course, on the third flight, which was in November 2004, they hit Mach 9.6.
Transitioning to scramjet.
This right here is a very good representation for those who've seen average. You can see the engine bottom. So this one has a turbine in it.
Mach 7, pushing 8, flight data. Receiving data is good.
Not 100% accurate, but it gives you an idea. You can see the leading edges start to glow red hot.
About 8.8, 8.9. Surface step rising.
At that speed, you could go from LA to New York in like 18 minutes. So that's why you don't want it to go too long. Otherwise, you're going halfway around. Very good representation. If you haven't seen it, absolutely take a look at the movie. So, what were some of the achievements of this program? I mean, it was the very first successful scramjet flight with its own free-flying body, right? Again, the body was designed to funnel air specifically into the engine. It was designed just for that. And they did win Guinness Books of World Records for their flights. So you can look it up and, and take a look at it. So there are very good benchmarks now. There's a lot of research information that a lot of companies nowadays are utilizing, so they're not starting from scratch. So what are some of the legacies of this program? So you're turning scramjet into somewhat of a proven technology, right? It's no longer theoretical, right? We've done it. We've proven it out 2 times, right? We've established a methodology, boost glide vehicles, right? So now, hey, here's an architecture that anybody else in the future can go ahead and build upon. And accelerate to materials and thermal protection research. So again, for those who are in that field, this actually helps. Now, a lot of it was based off of space shuttle thermal technology, because a lot of those like I said, thermal protection tiles was from the space shuttle itself. So that really actually does help the X-43 program. But now with the X-43, they added on top of theirs for future people. Now we're doing research into hypersonics themselves. So what are some of the future applications here? Now this one is a little bit, I guess, political. I've had a lot of people ask me, why are we so far behind on hypersonics? That's a yes and a no question. No, we're not necessarily behind because we did this decades ago. But yes, we are behind because we dropped the ball after that, right? Because it wasn't necessary, right? No one really cared after that point in time. Why is it kind of important now? Because of certain, countries and geopolitical instabilities forces you now to catch up, revisit some of this old technology and go back and say, hey, you know what? We need to catch up right now. So what you see here on some of these, right? Hypersonic cruiser, wave riders. You see new weapon systems, hypersonic weapon systems coming online to compete with some of these other foreign countries and adversaries. So there's a lot of applications, but not only just in the air side, but there's also applications on the space side, like manned space flight, so on and so forth. So this is very good research. I talked with an old professor of mine at the AIAA conference, Dr. Eugopoulos, and we chatted a little bit. His specialty is combustion. And so we were chatting a little bit about this, and he had the same sentiment about, we're not behind. It's just that they like it, then they don't. They like it, then they don't. So then funding goes up, research goes up, funding goes down, research goes down, and so on and so forth, right? So we're not necessarily behind. It's just a matter of we have to pick up where we're at before and continually develop it. Don't stop, right? For those in any kind of industry, once you stop something, it's very hard to restart. And it probably costs 10 times more than if you continued on. Right? Any questions so far? No? Yeah.
What was the top speed of the X-15? I can see it. Was it Mach 6?
I think it says Mach 6.7, something like that.
Yeah.
I don't know. So anybody that's worked on it before, tell me. That's 6.7? Okay. Yeah. Any other questions? Yeah.
What differentiates a scramjet and a ramjet?
So a scramjet essentially is supersonic airflow going in. Ramjet is subsonic. In simple terms, I'm not a combustion expert, but that's the simple term.
So wasn't there a lot of ground testing done at the ADC there in Tullahoma?
Yeah, there was a lot of ground testing done over there, but it was also a lot of testing was also done in the wind tunnels at NASA as well. Who's this online?
What's that? Oh, Kevin Burns.
Oh, okay. Thank you, Kevin, for the question.
Also, I believe that Mr. and Mrs. Markham are in the online audience, and they were the owners of Microcraft at the time.
Oh, they are fantastic. That's awesome.
What's the name? What's the name?
Kate was asking what was the name of again?
Oh, Mr. and Mrs. Markham. Fran Markham's father started the company, and he died in a glider accident. She took it over.
Oh, yeah. Well, I'll tell you what. Those people at Microcraft were fantastic to work with. They were an interesting bunch, but I like hanging out with them. They were great. Had a question? Yeah.
At the end of the flight, how does the vehicle basically land and get recovered?
Good question. You're right. I did not go into that. It does not get recovered. These were all single use, so it just crashes into the ocean. So they were not designed to be recovered at all. If you can imagine, recovering something like this probably costs more than just building another one. And that's pretty much where it ended up being, right? It's like trying to recover something going that fast and landing it that doesn't even have any kind of landing gears. So you're adding more weight and more complexity. So like, you know what? We don't have that much money or time. So single use, we'll just go with it. Yeah.
Then there wasn't really a case for examining the materials after the flight.
No, not necessarily. Because a lot of the materials was a lot of the, you mean the thermal materials, or well, a lot of it was based off of the shuttle tile. So a lot of the information was kind of already known. It was just a matter of how was this used on this vehicle, right? And was it placed in the right spots? So that way they get the correct telemetry and information from the sensors on board, right? If anything was getting overheated or so on and so forth. So,
There ever a potential for a commercial wider application, non-defensive or non?
yeah, so I forgot the name of a company. So there's a private company right now. Is it Boom? Boom, there you go. So Boom is one of those companies that's trying to revive, supersonic flight, right? After the Concorde. So there are certain companies that are looking to try to get back there. NASA is doing a lot of research. I mean, a lot of the problems right now is not so much the flight, it's the sound, right? Especially coming off from airports. No one wants that sonic boom. I mean, if you live in El Segundo, that would be your worst nightmare if something is landing, right? That LAX, you wouldn't be able to sleep at night at all, right? Whenever it's flying. So there are companies right now that are working on that. Not necessarily any closer to anything real in terms of flying yet, but there are companies working on that. So, but a lot of this is also going into, like, if you look at SpaceX, right? One of their use cases for the Starship is taking off and landing somewhere else, right? At a faster speed than flying on an airplane. Not necessarily, quote unquote, supersonic or hypersonic travel, but that kind of goes into that kind of thought of how do we get people to their destination a little bit faster. Yes.
So if the last flight was a failure, would there fit another vehicle produced?
I don't know. We only have money for 3. I'm sure they might have, but it really depends on the budget at the time, because there was only really 230. And if you kind of look at the trends over the years, NASA's just getting less and less and less and less money. So that was a bit of a toss-up. If the third one didn't really pan out, maybe there's enough for them to push forward because the second one was successful, as long as we understand what we failed on. Right.
It's going to go back to prioritization. Like if they wanted to build a hypersonic defense capability,
yes. Well, it would probably more or less be the military would take over that technology and take that program over. They'll just take what NASA has done, bring it into the closed side for defense purposes. And you've seen that right now, right? A lot of these hypersonic missiles now, so on and so forth. A lot of it was based off of X-43 and other kind of hypersonic research. So everything that we've done, again, it's just a basis of what somebody else has done or reviving. Yes.
Yeah, I have a question online.
Sure.
Yeah, could a vehicle like this scale to incorporate multiple scramjet engines? How difficult would it be for the aerodynamics to be able to accomplish the atmospheric funneling and so forth into the engines? And just to comment, I remember watching on NASA TV the live launching of the X-43 back in the early 2000s. So I recall NASA had that live, and I was able to watch that. So that was fascinating, and and your presentation's very interesting. So anyway, thank you.
So I'm not going to be able to answer the question the way you want, because I'm not necessarily an aerodynamic or combustion specialist. So I'm going to have to kind of defer that question off to the side. I'm more on the operations side of the house. So, but does anybody here know how to answer that question?
Well, there actually was there was some budget put out by NASA. There was some budget actually in the 2003 time period, early in 2003, because they approached us and we were looking at an X-43 Bravo and an X-43 Charlie, and I can't remember which ones, but we actually did a 6-month study on it. Okay, and actually we were going to expand the platform. Okay, and actually put gear to go ahead and try and land. And the idea was to go ahead and get 3 test flights out there. That was the talk at the time. But like you said, it's very, very true. Budget, money, et cetera, et cetera. And the money just ran out.
Yeah.
But there was very high interest in go ahead and doing that. And you know, that 2D plan, that 2D scramjet right there actually migrated into a couple of different studies at that time.
Right.
But the success of the 43 Alpha was very high at the 2004, 25 time, 2005 time period. Okay. And then it lent itself into a couple other different programs that are funded by different agencies.
Right.
And like you said, then it kind of resumed in the mid-teens because of, you know, activities happening from our friends in Southeast Asia.
Right.
So you're right. There was a dormant period. Okay, but there was a lot of study, and you know, it's all based on funding, and budget, etc.
Exactly right. But in the aerospace world, right? Funding changes on the drop of a hat.
Right.
What's your background?
I'm blocking up in front.
Oh, fantastic. Well, you know everything that's going on too.
No, but I you know what, I can add something that's
Sure.
really interesting. Is 2 days I was at a conference. I don't know if in your experience, maybe somebody online, Dr. David Glass of NASA of Langley, very instrumental in this program, okay, back in the day. And in fact, 2 days ago in Huntsville, he gave a half-hour briefing. He touched upon different topics, but one topic he touched upon, and this was very interesting, is the leading edge, which was actually developed by a company called MER, Dr. Cobble. What he said was, and he said this years ago, and then I kind of refreshed the memory to a lot of people in the audience, is that on this bird, on the 43 Alpha, what they did was for analyses, they used what's called, from the CFD folks, radiation equilibrium temperatures, okay, and it's a straight temperature. In reality, you over-designed it. So in other words, what he was saying was, on this guy here, it showed a much higher temperature level. In reality, on the ground test, it showed that the temperature level was considerably lower, and then the actual flight test data from the TCs and the embedded in the edge, it showed it even lower. I mean, to like half the temperature. Right. So what does that mean? Ooh, we over-designed this edge. And that was a lesson learned. It was really interesting what I said just 2 days ago out there in Huntsville on this Dr. David Glass.
And so, like that goes to your question: why did we not have to, recover it? Because we had a lot of sense from that, kind of get a lot of.
Yeah, and I could say this, that actually 2004, there was a program out there in that time period funded by a different agency, and it was called Falcon. Right? And the interest at that was taken upon the lessons learned here, is adapting it into a small craft, roughly about the same lateral length, okay, same span, and actually looking at high temperature materials. And there was thought, at least kind of a concept study done about 2 months long or so, and actually putting up little gear and actually landing at Roosevelt Roads, Navy base off of Puerto Rico, and costs, et cetera, et cetera, et cetera. So it was interesting, but actually taking something about that and actually put real tiny gear.
Do you remember? I want to say, it's been over 2 decades, but do you remember if? I do remember hearing some talk about them potentially like putting skids on it for recovery on a glacier. You remember that talk?
On a project we were working on at the time,
Okay.
we were actually considering putting skids, because if you put gear, if you put tires, you go to these types of speeds, how are you going to keep it cool?
Exactly.
Okay.
Yeah.
So skids, obviously the X-15, based on that, right? But the difference is on that is you buttoned up, you went off, you launched in air, and you went back down.
Right.
Okay. How do you do it with something that you're taking off horizontal takeoff, button up, keep cool, and come back down?
I remember, we were in a meeting, we were chatting with a bunch of the NASA guys, and they were thinking about putting skids on the top.
Yeah.
Then they'll flip, right? And then land with the top of the skids coming out from the top.
Well, coincidentally, we had a project going on at the time. We proposed it to the agency, and they didn't want to do it. But actually, the German World War II ME-163, the rocket planes, it had the boat tail. The boat, it was like a hull design. Company that actually decelerating and slow and landing on that front grass. But they wanted to see conventional gear. And we thought, walk, crawl, or crawl, walk.
Right, exactly correct. So as you can see here, I mean, there's a lot of technology that's kind of built upon this, offshoots here and there. So there's a lot of things that are happening, not necessarily things that are in the public for everybody to know, but there are a lot of things that's been happening, whether, like you said, it was either research in the background, not anything real hardware development, until somebody, hey, we're falling behind and we actually got to really do some hardware development. So really, everybody kind of needed that kick, I guess, in a sense. But that really is the end of my presentation. And I know I've been asking questions already, but is there any other questions anybody has?
I'd like to mention that the AIAA History Committee is planning a session at SciTech 2029 for the 25th anniversary of the last flight of the X-43.
Oh, that's fantastic.
So, yeah, there's enough time, it's a few years out.
Can you share more details on that? If you have any?
Yeah. The committee just decided that it was an important enough event that if we could organize a session on it from, various other committees, materials, propulsion, all of that, that would be good to have a session on the X-43. So it's in the planning stages.
Okay. Fantastic.
So if anybody wants to present a paper on the X-43 in 2029 at SciTech, that would be great.
You know what? If you're going, are you going?
I mean, not yet.
You can take this model if you can pack it up with you. It's a little large, but
I'll relay that to Dr. Glass.
Yeah, absolutely.
He was instrumental in Sandra Walker.
Yeah, absolutely.
As well.
Yeah, that would be great.
Very key on that.
Yeah, that would be great to get people that used to work on these, did a lot of research and operation, get them back in, into this. That'll be awesome. Any other questions anybody might have?
Nick online has a question.
Oh, yes. Nick, can you hear us? No.
So if I remember rightly, there was a scramjet experiment with the X-15, of which the scoop actually burned through from the heating. How did you be able to get that scoop to survive the intense heating?
So I'm not sure what the X-15's issue was. Do you know? Yeah.
On that program, but I think what I've heard that's true, it did burn off. It was
Right.
an experiment. I think it was on bird 3, X-15, the third one, if I remember correctly. I don't know.
Right.
It was where they had a dummy scramjet system mounted onto the X-15, and when they wanted to see what the aerodynamics and heating would be on it, and it burned right through the scoop.
That's right.
Okay. So, but with this vehicle in itself, again, I didn't do any of the analysis, but I've seen the engine itself. There's nothing any really special about it. It is metallic. So it's probably has to do with the materials that this engine was built versus the X-15. I don't know what the X-15 engine was built with. So anybody have any idea what it was built with potentially?
Well, it wasn't the X-15 itself. It was the vehicle that was attached to it. That the X-15 was something that could get it up to speed enough. And so my understanding is that hypersonic research with scramjets was suspended for a long time after that because they felt they had a materials problem that they were not able to overcome.
And AIAA has sponsored a bunch of good, I think it was in February, the last one on X-15. There's an author in the local area that spoke on that. I forget her name.
Oh,
Michelle.
they talk.
Michelle.
That's it.
They talk specifically about that issue too.
She covers.
Oh,
yeah, she's had periodic talks. And yeah.
oh, fantastic! I'm gonna have to read that. Any other questions online?
Try Nick, see if we can keep up.
Nick, are you still there? You had a
Yeah,
question?
I'm still here. Can you hear me?
Oh, yes, we can hear you.
Awesome. Hey, thanks for the great presentation. I had a question earlier regarding the scaling factor, and I think someone touched upon it. But I was at the National Museum of the Air Force last year, and I saw the X-36, which was another scaled model. And it brought me to the question, given that the X-43 is also scaled, do we see any issues with scaling up from R&D to a full-size vehicle? And this is a broad question for you, Dennis, or anyone else in the audience. Are there particular subsystems that run into issues, whether due to aerodynamics or just component structure, whatever it may be?
So there is, I mean, anytime you scale anything up, there's always going to be issues, right? Whether the materials, the structure itself, the weight, and depending on what your mission is, especially if it's for a manned flight versus unmanned, or what exactly you're trying to do. But there is always going to be some kind of issues that everybody will have to work through. But the good thing is that at least you have a baseline with this X-43 program, that you have an understanding of what might actually happen as you scale up. Like you said, there will always be some sort of issue. I'm not going to say that there's absolutely nothing. Anytime you do go up in size, something always does creep in, as typical engineering fashion. But again, it's not going to be as though you're starting from scratch. I don't know if that really answered your question.
Yeah, great. Thank you so much. I appreciate it.
Great. Is there any other questions online, Ken? Yes.
So I'm not familiar with jet engines and all that stuff, but what's the altitude limit of the vehicle? Because obviously you need to be pushing in an atmosphere. And from the first flight, you said that you had to go up in altitude. So did that impact, the ConOps?
No, so the ConOps in itself is this pretty much the same, other than instead of dropping at 20, you're dropping at 40. So the B-52 just flies a little higher. And so you have to change the trajectory a bit on the rocket. So, you're not going above the 100,000-foot level, right? So that's about it in terms of change in the ConOps and the flight trajectory. It was a generally pretty easy fix. It wasn't necessarily anything technical with the vehicle itself. So that's why we could do another quick launch relatively quickly versus spending a year or two trying to figure out what went wrong. Okay. Yes.
So why did they launch at 20,000 in the first place?
That's a very good question. We're not really sure.
They didn't have enough fuel on board, hurry, or what?
I've read through the NASA failure review board papers, and there was actually no mention that I could figure out on why they decided on 20 instead of 40.
You might hit a stray JetBlue with that altitude.
Well, that's why they had us go out in the Pacific, and I guess the test range out there in the Pacific. So we're flying out there where no plane should actually be, commercial planes.
By the way, in the movie, what altitude was Tom Cruise when he was off?
That's a good question. You know what? I don't know.
I don't know. I saw that movie once, and but they showed, but well, it was great. I remember one of the conferences. There was actually an admiral, a Navy woman admiral, and she said to a whole crowd of people, she said, "Don't get me started on all the inaccuracies." And the thing is, this is what resonates. I know they showed the altitude, okay, which claimed that he was low, and if he was low, that thing would have burned up. That's pure simple. So yeah, it's home.
Yeah.
But
the whole point is that you understand, you get the visual from the heating and the sound and all that kind of stuff. That's really what you get out of that. But yeah, I'm sure there's a lot of leeway in terms of Hollywood taking their.
You had a question about it? Yeah. No, yeah, you.
Yeah. My question is, you mentioned the appetite for development of this type of technology is cyclical.
Yes.
And my question is, where on the pendulum is it now? And what kind of advice would you offer to someone who's entering this this job market. And, looking forward to internships and ultimately a career there.
So the good thing for you is that we're on the rising end of the pendulum at this point in time. If you said this maybe 4 years ago, we're probably kind of at the bottom end, but it is rising just due to the fact, again, there's other countries and adversaries that are having this kind of technology. And number one, you don't want to be the quote unquote, powerful country without it. So here you go, right? You're on the rising end of the spectrum. In terms of internships and the job market, it is tougher than it was previously. I'm not going to say it's impossible as you see out in in media and all that kind of stuff. The difference right now is that the companies no longer have to just pick whoever they want, right? Now they're able to pick and choose the right skill sets that they really want versus just scooping everything up and hiring everybody. And so in that sense, if you have the knowledge and you have the skills of what they're looking for, it probably won't be as hard for you to get a position, right? If you're graduating from college without much experience, it will be a little difficult, right? So it really kind of depends. In previous years, and you saw this at like software companies where they're just going out with just a big dragnet, just pulling everybody in. Whether they have a position or a job for them, they don't care. They're just making sure that their opponents don't get talent, right? And so they'll just put them away. And I remember at one time, Northrop, we did this on one program. It's an aircraft program, and a lot of people were stationed in Florida, and they were sitting around playing ping pong for like 6 months in a warehouse. They had no job for them, right? But because they knew the program was coming, they didn't want them to get scooped up by somebody else. And so pretty much most of those people ended up quitting because they got bored, right? And they're young, they weren't getting any experience and stuff, so they ended up, leaving. So now, because money is tight, there's a lot of people out there that they can be more judicial in terms of who they pick and choose. So yes, you do kind of have to be on the higher end of the spectrum in terms of skill sets, but that's not to say that it's impossible to do. But it is harder than the good old days 5, 6, 7 years ago. Yeah.
No, I was just thinking a comment that there's no possible way, based on what I've heard, that there could have been a manned flight at Mach 10 as represented in.
Not with this vehicle. not with this vehicle, that's for sure. Yes.
I saw that it says hydrogen powered. Was it liquid or gas?
So the hydrogen and the xylene, they're all liquid.
Yeah.
What's that?
You couldn't get enough
Yeah.
gas in there.
Yeah, it's all liquid. Yeah.
I just want to make a comment on internships and things like that. There's one thing that's happening right now in the industry, and that is the mature and older generation with the experimental experiences are retiring.
Mm-hmm.
They're no longer there, and so there's kind of a generational gap, which should encourage the younger graduates sort of thing, because these companies are looking for just people with the basic skills.
Yes.
And then once you're there, they do, distribute according to their needs on various programs, things like that. And there's another reason people are hired and then they wait around, and that is they have to wait for their clearances from the government. That can take a while at times.
So that's a good point, Lynn. So if you have a position or you have an internship, I remember at Northrop, I was pushing one of our big programs at Northrop to give our interns security clearances so that when they graduate, we can plug them right in versus, again, waiting 16, 18 months, right, minimum, if there's no issue to get cleared, right? And so there are companies right now that are giving those kind of clearances, Northrop being one of them, now to interns. So if you can find one of those high value internships, that essentially is a golden ticket for you. If you walk in there and you have a security clearance already, a high level security clearance, that's worth a lot. They'll teach you the rest.
Hey, by the way, another bit of advice, if you have an internship at all, it's worthwhile just to inquire about what it would take for you to get a clearance. Even if you're not, even if they don't see a need for it at the time, they would start to think it's kind of a need, and all like, oh yeah, we should be thinking about it.
I could add just a bit of trivia for a manned flight at Mach 10. The SR-71, they measured the windscreen temperature, and it was a little over 400 degrees at Mach 3. So at Mach 10, because one of the SR-71 pilots finally dared and touched it and just about burned a hole in his glove.
Right.
So at Mach 10, it would be a whole different environmental issue to have a manned person and have a windscreen right in front of it. I think probably be like 1,500 degrees.
Yeah.
So might be very difficult.
It's going to get a little toasty in a cockpit.
So
I have a comment online.
Yes,
I have
go
a comment
ahead.
online. I don't understand because the space shuttle on reentry goes. You're incoming at Mach 25, and it had plenty of front windows. So obviously there must be some ability to
I'm going to assume it's
maintain
because
integrity.
There is glass that can take it, but the space shuttle doesn't come in with their windscreens forward.
Right.
You know, it's largely shielded.
Right. So it's kind of falling belly first, almost kind of coming down.
So before there was talking about generational gaps in the 2000 Air Force Scientific Advisory Board report, Wine Withered Hypersonics, it states that the United States tends to cycle in and out of hypersonic research, and in doing so seems to do it at a gap just large enough where we lose the knowledge that we've gained as a new generation is coming in.
Yes, that is. You know, it's not, in my view, being in the aerospace and defense industry for so long, that's not even just for hypersonic. That's for everything. That's just the way this industry works, because a lot of our money does come from the government. And so as the government purses go in cyclical mode, pretty much every program gets reevaluated, gets delayed. And the longer you wait, the more you think about, well, the original design no longer works because new technology comes and I got to redo it, which means I need more money. And so then problems just start to escalate. And then now you get to a point where it's more than what the original program cost. So now you're over budget and we're going to cancel you. And so then you get canceled and then you're back to the lull down at the bottom of now you're waiting for the next issue that we have to build a hard piece of hardware for to solve. So that's just the way the aerospace industry works in terms of a cyclical cycle. It's not just in the aerospace, but a lot of the universities that do research, like the professors, you know, who do combustion and all that, they're saying the same thing, right? As the government loses money for funding, their research goes down, it goes up, goes down. And so, you know, their research that a lot of these companies like Northrop and all that bases it on, it all goes up and down with them. So the academic world actually gets hit just as much as, you know, the private companies or government institutes like NASA and so on and so forth. Now, that's not to say, you know, some of these shadow groups don't get more money, but, you know, that's for another topic and discussion later. Anybody have any other questions?
Angel online seems to be.
There's more questions online?
Angel, do you want to speak out?
Yeah, just want to chime in. To anyone that's in the event and online, if you guys work in hypersonics, I'd really love to connect. Look forward to getting into that industry sometime soon. I specialize in aerodynamics, so that's something that I would like to get into. My LinkedIn is also on there as well, so I don't know if you guys can pull that up. If you guys want to connect, the link is on there. If you guys just type that link into Google, you guys will be able to find me. Thank you.
Okay, thank you very much. Yes.
Benefit
Yeah,
folks here.
absolutely.
The JATO office, Joint Hypersonic Technology Office, okay, part of the Pentagon. They run a program, they run an effort, okay, it's called University Consortium of Applied Hypersonics. Okay. It's been around for about 5 years. Okay. And actually, they just like 2 months ago, they just had some changes at the top. They're going to revamp it. But what I'm saying is, for those who are interested, I mentioned this stuff just over here earlier this morning, and what it is it's based on that. One of its objectives is to get more folks, especially on the university side, involved in this, and actually working with industry and the government as well. Okay, and so I encourage people to check the websites. It's an open website, UCA.
So did you hear that?
Can you repeat the name again?
UCA, UCAH.
UCAH.
University Consortium of Applied Hypersonics. And what it is, it's over the 5 years of its tenure so far, it's involved like over, I don't know what they claim, a lot of universities. I mean, over 50, maybe over 100 or so, maybe not that.
Can you give a little more information on like what's their purpose of what they're doing?
Okay, the purpose was the government JATO, that is, and it's not their only function, but JATO, Joint Hypersonic Tech Office. They're trying to get more college-based, whether undergrad, graduate, etc., students involved, and it's very relevant. Okay, they see what's happening overseas, and they say, "Wow, the United States needs to be more proactive on this." So some smart people got together, 5, 6, 7 years ago on this, and formed this. They're going along for 5 years. And it involves universities working together in tandem with industry under specific sciences problems. In it could be on controls, it could be on structural materials development, it could be on CFD, etc. Computational fluid dynamics, etc. And it's involved a lot of students, and a lot of these students have migrated over to industry afterwards.
So it's like a joint with the Academic Institute for Research, and so they'll provide funding to the professors doing these kind of research and stuff like that. And then students who might work for the professors get to be participants in this as well. Do they sponsor any kind of competitions, like design competitions and stuff like that?
Yes, they do.
Okay.
And they just had the event in Huntsville this past week.
Okay.
There's another, I hear they're planning on another event in November, probably in Alexandria, Virginia, as they have before.
Right.
And it's a great place to. They have a lot of the students come up and talk about their status on their projects, etc. And we're working with company X or whoever, and where they're going and what they're going to be doing, what they're planning for the next year, etc. They're building this, they're testing this, etc. So it's a great group for workforce development.
Yeah. So that's an awesome piece of information right there. So I hope everybody wrote that down. If not, maybe Ken, you can send that information out to everybody if they didn't catch that.
The program is managed by Texas A&M.
Exactly. Yes, it is.
And
Yes.
two of the major universities that are participating is University of Tennessee Space Institute with all its hypersonic labs. And the other one is the Vanderbilt Aerospace Design Lab in Nashville.
Purdue is a big active player in it. Texas A&M, yes, Dr. Rodney Bowersox.
But just to add on that, I'm glad you brought that up because there are a lot of universities like USC, the Space Force down the street gave them a challenge on like 6 or 7 different issues, and they had USC engineering teams break up and try to solve those issues and present it to Space Force personnel. And so, if they like it, they will give you some money to continue that kind of research and so on and so forth, see if it leads to anything. So if there is anything like that at your school or where you're at, definitely participate in those kind of things. That would get your foot in the door, that you're working with industry, even though you don't have, a specific job, right? But you're working on solving a real problem that was actually given by people in the industry. That would be a great foothold as well. Or even participating in any kind of like school programs or projects. Like, for example, if you're into space, Cal State Long Beach has CubeSats. Well, actually, a lot of universities do CubeSats as well. join one of those. I'm advisors to a number of these schools, right? And so you get to meet industry people as well, because we're teaching you how we do things in industry. So that also gives you some credibility when you're going out looking for jobs, that you're actually working with people in industry. And it's not just necessarily books, but people actually teaching you what we are actually doing out in the real world. So that'll give you guys a leg up if you're, looking to do that kind of work.
Just another point, in my experience, there are a couple of things when you are in a company. If you want someone to be your mentor, he may be a vice president, he may be chief engineer, just ask. The majority of these people are more than happy to actually mentor someone who's interested in being mentored. The other thing is, you could, even if you're not in the geographical area or associated with the organization, if you're interested in Jake, for example, contact them and say you're interested and you'd like to participate.
Go to all these events, not necessarily job fairs. I don't think job fairs is the best place to go find anything, because you're competing with tens of thousands of people. You being here at this event, it's you plus maybe a handful of other people, meeting people who've been doing this job for a very, very long time. You go to industry events, conventions. If you want to even meet the Space Force, they're at like all of these Fleet Week. They're even there. They have a booth and they're talking about careers, and meet the people there. They're great. They love to talk to you, to learn more about you, and they love to share what they're doing. So, be a little bit wider in terms of where you go to talk to people, right? Like I said, this is a great step being here and talking to us, right? And again, you can see most of these people, you probably never see them at a career fair, right? Unless, I'm actually looking for people in my group, but short of that, even then I probably wouldn't go. I just have, some other people, HR give me those resumes.
Yeah, you're really helping the recruiters by expressing to them what your interests really are and what you're passionate about. And they appreciate that.
Because the one thing that I always tell people, because when I hire people, I usually do a 3-step process, right? I send my first thing is my administrator will come get you, and she's the first test, yay or nay, right? If you can't work with her, then that's a no, right? Second is an interview with me and a couple other people in the room. And the third one is I take you on a tour. I want to see how interested you are. I've seen some people very, very interested, asking questions nonstop. And I see other people walking around yawning, even though they did great in the interview, technically awesome, right? So the bottom line is that if you graduated, you're smart to a certain degree, right? I hire you for your personality. I can't teach you that. I can teach you everything else, as long as you're willing to learn. Okay? So remember that when you guys go out and look for positions, is that they're looking for personality, but they're also looking for certain, at least a baseline of knowledge, and then the rest they'll teach you. Because we know a lot of the stuff that we do out in the real world is not necessarily taught in school. I would probably say only like single-digit percentages, right? Unless you're doing research. At that point, research is just research, right? Any other questions? Anybody else? Anybody else online? No? Well, then thank you very much. I really appreciate everybody coming by and listening to me, especially on your Saturday. I know your teaching is special. Oh, yes. I did read your program this time around.
I'm gonna contact Jado myself. Ah, there you go. Anyway, thanks, Dennis.
Well, thank you very much.
Really appreciate it.
Thank you.
All right, thank you. Thank you, everybody.
we have coffee in the kitchen and the soda on the table in the refrigerator and enjoy the refreshment.
If anybody have any other questions, I'm still here. So.
Yeah, post online. If you still have questions, you're welcome to speak out. We will stop the recording now.
Oh, that's 1 year.